Choosing how dual-channel spark ignition systems reduce ignition failure risk in large industrial furnaces usually becomes difficult when product claims sound similar. The article narrows the decision with concrete context. A 5-factor risk matrix links 2J, 2500V, 6-spark output with 10 checks for safer furnace ignition. It also raises a second point buyers should keep in mind. A spark may look like a small component event, but failed ignition can interrupt production, increase unburned fuel risk, and force maintenance teams into repeated. A 5-factor risk matrix links 2J, 2500V, 6-spark output with 10 checks for safer furnace ignition. Large industrial furnaces create a difficult ignition problem because the first few seconds of startup combine fuel admission, air movement, purge logic, flame detection, and operator confidence. A spark may look like a small component event, but failed ignition can interrupt production, increase unburned fuel risk, and force maintenance teams into repeated checks under time pressure. In this context, dual-channel spark ignition is not simply a feature count. It is a design method for reducing single-path dependency in a system where cable condition, electrode position, voltage stability, burner sequencing, and flame feedback all affect the same startup result. A procurement team evaluating high-energy igniters for furnaces should therefore ask a system question. Which ignition design makes failure easier to prevent, easier to diagnose, and less likely to stop the line? The answer depends on specifications such as stored energy, output voltage, spark frequency, input range, operating temperature, and channel architecture. A product such as the Tingyan TYQ 2-6-2, described with 2J stored energy, 2500V output, 6 sparks per second, dual-channel output, and DC 16-36V input, is useful as a concrete example because it shows how procurement evidence can be tied to furnace reliability rather than presented as isolated data. Why furnace ignition failure is a system-level risk. 1.1 Failed ignition is rarely caused by one component alone. A large furnace ignition event depends on timing. Fuel must reach the correct zone, air must support a stable flame front, purge logic must clear unsafe mixtures, the spark must occur at the right position, and the flame detector must confirm combustion before the control system allows the sequence to continue. A failed start may be reported as no ignition, weak spark, flame loss, or repeated trial for ignition failure, but the underlying causes can sit in several places at once. 2. Why single-path ignition creates avoidable diagnostic delay in a single-channel system. A fault in a cable, connector, electrode, output terminal, or local wiring path can stop ignition without giving maintenance teams a fast comparison point. The team must isolate the power source, check the igniter, inspect the cable, clean the electrode, verify the burner, and then repeat the startup sequence. Operators may become uncertain whether the fault is electrical, fuel-related, or control system-related. 2.1 Fuel condition, purge timing, and flame feedback should be evaluated together. A reliable troubleshooting model should not treat the igniter as separate from the burner management system. The purge sequence, ignition trial period, fuel valve timing, and flame supervision logic all determine whether the spark has a real opportunity to create a stable flame. Dual-channel ignition helps most when it is integrated into this wider sequence rather than installed as an isolated spare output. How dual-channel spark ignition works in industrial furnaces. 2.1 Practical meaning of dual-channel output. Dual-channel output means the ignition device can support 2 output paths. Depending on the system design, those paths may be used for redundant ignition points, separate burners, staged ignition logic, or maintenance comparison. The engineering value is not automatic redundancy in every installation. For how dual-channel spark ignition systems reduce ignition failure risk in large industrial furnaces, the safer decision is to compare the article's requirements against real supplier evidence, not only the sales description. Before purchase, teams should confirm the operating conditions, specification limits, quality checks, support expectations, and any trade-offs that could affect daily use.